This video is about optimization. That's where you try to achieve the best outcome possible given certain conditions. In this case, we are minimizing area. Specifically, a rectangle is to contain 24 square inches of print. The margins at the top and bottom are to be 1.5 inches. The margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So understand the diagram. The blue rectangle represents the print, and the yellow rectangle represents the entire paper. So that's why I have the little 1.5 here and here representing the upper and lower margins, and the 1 here and here represent the 1 inch margin on the left and right. Usually when you do an optimization problem, you will have to write two equations, a primary equation and a secondary equation. The primary equation will represent the quantity that you are trying to maximize or minimize in this case. The secondary equation will represent some other information that you're given. So in this case, we are trying to minimize the area of the entire paper. So the area of the yellow rectangle. However, in order to make an equation for that, we are going to need dimensions for the width and height of the paper. So I've labeled the width of the print area to be x. So how wide will the paper be then? Well, since the margin on the left is 1 and the right is 1, the width of the entire paper should be 2 inches more than the width of the print. So we can call that x plus 2. In a similar way, since I've labeled the height of the print area y, then the height of the entire paper should be y plus 3 because the margins of 1.5 and 1.5 total an extra 3 inches. Now we are ready to write the primary equation representing the area of the paper. So we know, of course, area is base times height or length times width. So that will be x plus 2 times y plus 3. So there's your primary equation. Now, how about the secondary equation? Let's look for an additional piece of information. The rectangle is to contain 24 square inches of print. That means the blue rectangle is going to have an area of 24 square inches. So that means xy, the area of the blue rectangle, should equal 24. Notice that the primary equation has two variables. We need to make this in terms of one variable. So we're going to use the secondary equation and rewrite it to get one variable by itself and do a substitution. Dividing both sides by x, we get y equals 24 over x. Now we can substitute this into the primary equation, and we will have a is equal to x plus 2 times 24 over x plus 3. Notice that now we only have one variable. Let's just keep going and simplify this as much as possible. I'm just going to double distribute right here. So x times 24 over x will be 24 because the x's cancel out. And then x times 3 is 3x. Now 2 times 24 over x is going to be 48 over x. And then 2 times 3 is 6. So combining like terms, I'm going to have 30 plus 3x plus, I'm going to go ahead and write 48 over x as 48x to the negative 1 power, so I can do the power rule easily. So we need to minimize the area of the paper. That sounds an awful lot like finding the extrema. And how do you do that? Well, you do the first derivative test and use that to identify where the function is increasing and decreasing, and that will tell you where the minimum is. So let's find the first derivative. The derivative of 30 is 0, so that's gone. The derivative of 3x will become 3. And now the power rule, negative 1 times 48 is negative 48. I'll just switch that. And then we have to reduce this by 1, so it'll be negative 48x to the negative 2 power. So the first derivative is 3 minus 48 over x squared. Now we need to find the critical numbers by finding where the derivative is equal to 0. We also need to pay attention to where the derivative is undefined. Because that is also a critical number. So first, where the derivative is 0, we will just set this entire expression equal to 0. Adding the fraction to both sides, we get 3 is equal to 48 over x squared. Now, when you have a fraction equal to a number, we are allowed to swap these. So this will become x squared is equal to 48 over 3, which means that x squared is equal to 16. If you take the square root of both sides, that will give us x is equal to plus or minus 4. Remember that x represents the width of the print area, and you can't have a negative width, so this is going to be extraneous. Now let's look back and think about where a prime is undefined. That'll be where the denominator is equal to 0, so we should have another critical number when x squared is equal to 0, which of course if you take the square root means that x is equal to 0. So that's another critical number. So let's put these numbers on a number line and do some test values. So here are my two critical numbers on the number line, setting up our intervals that need testing. Notice that I put the 0 right on the edge of the number line. That's to symbolize that 0 is the end of the domain. You can't have negative widths. So I'm putting that right on the end to show that we're not going past that. So we will only have two intervals that need testing. So in the first interval, let's pick the number 1 as a test value, because that's just easy to use. And in the second interval, let's pick the number 10 actually, because it's just easy to do the math with the number 10. All right, so if we evaluate the first derivative at 1, that's going to be 3 minus 48 over 1 squared. So that'll just be 3 minus 48, and all we care about is, hey, that's a negative number. That means that the original function will be decreasing in this interval. Now let's look at 10. 3 minus 48 over 10 squared. That'll be 3 minus 48 over 100. And dividing by 100 means you move the decimal point 2 times to the left. So this is 3 minus 0.48. And obviously, that is going to be a positive number. That tells us that the function is increasing throughout this interval from 4 to infinity. So we can see that indeed the value of 4 produces a minimum area of the paper. So we have found that x equals 4. We need to find what y is. Let's use the secondary equation. And we already have y by itself. So if we let x equal 4, then y is going to equal 24 divided by 4. So obviously that means that y is equal to 6. So x equals 4 and y equals 6. But these are the dimensions of the print area, the blue rectangle. We need the dimensions of the paper, the yellow rectangle. So the width of the paper will be 4 plus 2, and the height of the paper will be 6 plus 3. That means the dimensions of the paper will be 6 inches by 9 inches. And remember, these are the dimensions of the page that cause the least amount of paper to be used.